Welcome back to DeepVisus, where vision meets depth. I'm your host, and today we're diving into an incredibly thought-provoking book, probably approximately correct, Nature's Algorithms for Learning and Prospering in a Complex World by Leslie Valiant. Have you ever wondered how life, in all its complexity, manages to learn and adapt so effectively in a world that is constantly changing and often unpredictable? That's the core question we'll be exploring today. How can complex biological mechanisms learn and evolve given the inherent uncertainties and limitations of our world and the resources available to us? Valiant, a renowned computer scientist, proposes a revolutionary idea that the very essence of life, from evolution to individual learning and intelligence, can be understood through the lens of ecorithms. So, what exactly is an ecorhythm? Think of it as a special kind of algorithm, a set of step-by-step instructions that doesn't rely on being perfectly programmed in advance. Instead, ecorithms learn by interacting with their environment, extracting the knowledge they need to behave effectively. They're like self-improving recipes that adapt to whatever ingredients and conditions they encounter. This stands in stark contrast to traditional algorithms, which are typically designed with all the necessary expertise pre-encoded. At the heart of Valiant's framework is something called the probably approximately correct, or PAC, learning model. This isn't just a fancy term, it's a quantitative way to understand how these ecorithms acquire knowledge. The probably part acknowledges that there will always be a small chance of error due to bad luck with the data, what Valiant calls misfortune errors. Imagine flipping a coin 100 times and getting all tails. It's possible, but highly unlikely if the coin is fair. The approximately correct part, on the other hand, accounts for rarity errors, the possibility that some rare but significant information might be missed in the learning process. The brilliance of PAC learning is that it provides a way to control these errors, allowing us to drive them down to arbitrarily small, though never zero, quantities by increasing the amount of learning effort and data. This quantitative control is absolutely crucial because if good predictions required an infinite or exponentially massive effort, then it wouldn't be a realistic explanation for how life copes in our finite world. To illustrate this, Valiant uses the simple analogy of an urn filled with millions of marbles, each with a number on it. If you draw just 100 marbles, can you accurately determine all the numbers present in the urn? Not without some assumptions. But if you assume there are only a small, fixed number of types of marbles, say 5, then drawing 100 marbles allows you to confidently predict a high percentage of the urn's contents. This seemingly simple example introduces two fundamental assumptions for PAC learnability. The invariance assumption, which states that the environment during learning is fundamentally similar to the environment where the learned knowledge will be applied, and the learnable regularity assumption, which means that the patterns or criteria we're trying to learn are actually detectable and acquirable with feasible computational effort. Now, where this gets really interesting for us at DeepVisus is the connection between PAC learning and evolution. Valiant argues that Darwinian evolution itself can be understood as a form of PAC learning. He directly addresses what he calls a gap in traditional evolutionary theory, its inability to quantitatively predict the rate at which complex mechanisms evolve or are maintained in changing environments. By treating evolution as a computational learning mechanism, we can analyze its behavior using the same quantitative framework as PAC learning. Valiant introduces the concept of evolvable target pursuit. Just as a student pursues a learnable target, a species pursues an evolvable target, a beneficial function or behavior that can be achieved through evolution. This pursuit is driven by an explicit evolution algorithm that ensures convergence towards the ideal function, provided it belongs to a sufficiently simple class. The target of evolution isn't some grand, ultimate design, but rather the local objective of increasing performance or fitness in a given environment. This performance is defined mathematically as the correlation between the organism's actual behavior and an ideal function representing the most beneficial action in every possible situation. However, evolution operates under a unique constraint. It relies on Darwinian feedback. Unlike a direct learning algorithm that can immediately adjust its hypothesis based on a single experience, evolution makes changes through random variations, mutations, and then selects the variants that show aggregate statistical superiority in performance over many experiences and generations. This is a more circuitous and potentially less efficient form of learning, akin to what's known as the statistical query (SQ) model, where information is gained only through aggregate statistical questions, not individual examples. This leads to crucial insights into the limits of evolvability. Valiant demonstrates that some functions are provably not evolvable within this Darwinian model, even if they are PAC learnable by other means. For instance, monotone disjunctions, a type of Boolean function where variables are not negated, like x or y or z, can be evolved, but parity functions where the output is true only if an odd number of variables are true cannot. This is a significant finding because it suggests inherent computational impediments to evolution for certain types of complex patterns. The good news is there appears to be no biological evidence contradicting this theory, with parity functions seeming biologically unnatural. So, to return to our initial question, how can complex biological mechanisms learn and evolve given the inherent uncertainties and limitations? Valiant's work suggests that it's through Ecorithms operating under the principles of pack learning, where evolution itself functions as a constrained form of learning based on statistical aggregation over generations. The impressive complexity of life isn't a miracle, but the result of these powerful, yet bounded, computational processes that learn and adapt over vast timescales and populations. It provides a quantitative, mechanistic explanation for how life can cope in a complex, theoryless world. And that brings us to the end of another fascinating episode of DeepVisus. We've only scratched the surface of Leslie Valiant's profound ideas, particularly his vision of how computation shapes our understanding of life. Stay tuned for future episodes where we'll continue to explore the fascinating world of the brain, mind, and intelligence,